Folks, how we doing? Picking up with this second day in our kinetics. And so we've spent some time talking about these reaction orders as kind of mysterious and elusive as they may seem, right? They just kind of appear as this number to us for now, right? Something's either first order or second order or zero order or third order. And so we really want to uncover now what that means. And so we're going to specifically go one by one, talking about first order, second order, and zero order reactions. Those are the only type of reactions that we're going to discuss in this class. So here's our first example on first order reactions. And this is our generic, right, extremely generic first order reaction. One single A molecule goes on to form products. For now, we don't care what the products are because once again, in kinetics, it's all about the reactants. And what we can also recognize here, or what we should start recognizing, because we're saying we know this is a first order reaction, and of course, this is totally, this like fictitious generic example. But all the same, if we're going to say this is a first order reaction, that means that for one, this has to be what we would call an elementary step, meaning that might not be the total reaction, right? We don't know what's going on with the products. Perhaps the products can go on and continue to react. But what we can say confidently, knowing that this is a first order reaction, involves only one molecule. That's truly what makes this first order. There's only one molecule involved, and we can see that. A goes on to form products, at least one reactant molecule. Okay, so if we were to look at the rate law, and I'm here calling this the differential rate law. That's for the calculus lovers. We could just kind of think of this as the rate law, okay? So rate equals negative delta A over delta T, and that equals K times A to the first power. Very simple rate law, okay? If we were to apply our calculus, we would get what we call the integrated rate law. And we're not going to do that in this class, and I'd be happy to show you all, for those of you that have taken calculus, more than happy to show you where this comes from, but I'm not going to hold you responsible for that. But you do need to recognize this integrated first order rate law ends up taking this natural log form. Okay, so let's describe everything we've got here. So this A at time t, so that would be concentration at any time denoted by t. Okay, so this t and this t correspond to each other, okay, time. And that could be in seconds or minutes or hours, okay, years, whatever we want. So there we can see negative k times t plus the natural log of A initial, and that A initial is our starting concentration, okay? So now, if we were to look at these equations, what we would find in a first order reaction, and this is one of the telltale signs that I want you to be able to recognize, the graph needed for a straight line. Okay, so if we were to plot just concentration versus time for a first order reaction, we would actually see that it's an exponential decay. So let's write that down, exponential decay. And so that is actually something that is true and observed for all first order reactions. These are exponential decays. So we could talk about biological decay or even biological growth. Those are exhibited to be exponential reactions. So now we actually could go on and conclude a biological growth or a biological decay is a first order. We're going to see other examples of first order reactions throughout this class, but for now we want to recognize it involves one molecule or one mole of molecules, right? So now, what if we took the natural log of that concentration as indicated by this graph? Well, you can see now that gives us a straight line. And the reason why we like doing this integrated rate law, I'm going to rewrite this over here, because as you know, we love getting best fit lines in chemistry. So this, if we kind of break this down and look at this for a minute, this becomes y equals, and that's going to be negative mx plus b. Okay. So in this case, so these two data sets are the same data set right here. So you can see when the time was 0, I just kind of did this as an arbitrary fictitious example, right? The concentration was 1 molar. So now if you look at this intercept here, it's 0.0, and that's because the natural log of 1 is 0. So if we weren't starting at 1 molar, like let's say we were starting at 0.1 molar or something like that, then our y-intercept would be the natural log of whatever that starting concentration is. Okay, and as you can also see, a reason why we would want to do this process is because now if we fit this to a trend line, my slope equals the rate constant. So we have a negative sign right there, right? But we should recognize rate constants are positive. And so that negative sign indicates that it's decreasing because it has a negative rate as a reactant. So now if we look at the units, okay, one thing we should recognize whenever we have natural logs, those the number inside a natural log will cancel. So if we look at our units here, this is KT, so those units have to cancel. And so if time is expressed in seconds, so we'll say T equals seconds, that means the unit of a first order rate constant is 1 over seconds. And that kind of makes good sense when you think about this from the perspective of first order reaction being a 1 molecule reaction. Its rate constant has units of frequency, right? This is a 1 over second, which is a frequency unit. So we can think of this rate constant as the frequency at which this A molecule decays, okay? So we could also talk about other things in a first order reaction, specifically the time constants. And the only time constants we're interested in for this class is half-life. And you've probably heard of half-life before. So that's the time required for a reactant to reach half its original concentration. And as it turns out, for a first order reaction, it has a special equation, T1 half, it equals 0.693 divided by K. Why 0.693? Well, because 0.693 is the natural log of 2. That's where that comes from. So if we wanted to be even more precise with this equation, we could say T1 half equals the natural log of 2 divided by K. And I'm not going to really talk about where that equation comes from, but if you're interested, if you want to see where this comes from, I'd be happy to show you. So now there's something rather interesting that happens in a first order reaction. Because it's this exponential decay, if you think about it, there's actually an infinite number of half-lives for a first order reaction, right? We get, if let's say we're starting at 16, we go half of that gives us 8. So then a second half-life of that would take us down to 4. And a second half-life of that would take us down to 2, and then 1, and 0.5, and 0.25, and on and on and on and on. So we actually see deep connection between first order reactions and equilibrium, because at least with some first order reactions, this will eventually stop and reach some type of equilibrium. Okay, that's not always the case, but a lot of the times we can look at these equilibrium type situations where we get a constant concentration and recognize the reaction has stopped because some equilibrium has been achieved. Okay. All the same, still very useful to be able to calculate one half-life as a means of seeing how fast the reaction will be. So hopefully it makes good sense that if you have a big half-life, it's a slow reaction. And if you have a little half-life, it's a fast reaction. And now if we look at the units here, we know natural log of 2 is unitless. K has units of 1 over 1 over seconds, and that just equals seconds. So that's why we can put our rate constant in 1 over minutes, 1 over hours, 1 over years, whatever we want. Because then when we use that to calculate a half-life, that will give us a half-life in minutes or hours or days or years, depending on what's appropriate for our reaction. Okay, next video will be on second order reactions.